and once you have one of these high mass stars, they will generate iron in their core as a result of these fusion reactions, and after that there will be a supernova explosion, right? And then we discussed about how that particular supernova explosion happens and the complete process. And at the same time, there is another type of supernova which we called as type 1A supernova, which happens as a result of having a companion star close to a white dwarf, where you accrete matter from the normal star that is very close to a white dwarf, and then by accreting those matter, the whole carbon will ignite in the white dwarf, and we call that type of supernova as carbon detonation supernova, or a type 1A supernova, right? And then we also talked about nova. Nova is when you have a white dwarf, and when enough material, or especially hydrogen, is accreted towards a white dwarf again. These the accreted hydrogen will go to a thermonuclear fusion on the surface of the white dwarf, which will make it brighter for some time and then faded away. And this is actually called as a nova. And then there is a difference. There are differences between type 2, type 1A, and a nova, right? And in order to have a type 1A supernovae, what you need to have is this accreted, the matter should exceed this Chandrasekhar limit, right? The mass should exceed the Chandrasekhar limit. So that is the limit to have a type 1A supernova, right? And this is what we discussed in the morning. And so let me share the PowerPoint from that slide. Right, so I have shared the PowerPoint slide. So I assume that all of you can access the PowerPoint presentation now. And if you can't access, please let me know about that. And also, while I am teaching, if any of you have a question, you can, at any time, you can ask about that. You can stop me and ask it, and I don't mind that. And at the same time, if you prefer, you can use the chat window to send me any questions so that I would answer those as well, right? Now, so where we stopped is right here. So we discussed that specifically about type 1A supernova, because these type of supernovas are taken, considered to measure the distances, right? The idea is, as I discussed in the morning, if you can observe one of these type 1A supernova in a distant galaxy, basically you can use that type 1A supernova to measure the distance to that particular galaxy, right? Now let me show you an example. So first I need to go from. So I will upload this note that I'm going to show you right now to the LMS as well. This is based on distance indicators. So let me share this with you. I guess you can see my shared screen right now, and this is an HTML file which I this is created from something called Jupyter Notebook, and this note specifically talk about different kinds of distance measurements, and I don't want you to know each and every point right here. However, there are a few things. So the first one that we use to measure the distances in astronomy is trigonometric parallax. Yeah, we have discussed about this, so I'm not going to talk about that again. The idea is you can use this equation right here, d equal 1 over p, straight away to yes, d equal 1 over p, where you measure the parallax angle in terms of arc seconds, and then you can substitute that value right here to find the d, that is distance. Right? From this way, you can measure the distances up to 500 parsecs, right? And 1 parsec is equal to 3.26 light years. And we have discussed these things in very early lectures. If you can't remember, you can go and get it. Now, there are specific satellites that we use to launch to measure these parallax angles for stars in the Milky Way, right? And one of the latest launches like that is this particular satellite, which we called as Gaia satellite. So this was launched in 2013 and was operating, as far as I remember, until 2018. And this was able to measure actually parallax angles of 1 billion stars in our Milky Way, and which means we know exactly the distances to these 1 billion stars, because the measurements made, parallax angle measurements made by this particular satellite are very accurate, right? And before this, we had another satellite called Hipparchus, which is also used for the same purpose to measure the parallax angles. Now, the distance limit that we have from this satellite is 9 kiloparsecs, right? And so it is actually a little bit more than what I have mentioned here. And then there is another way of measuring distances, which we called as spectroscopic parallax. And this is also something that you can get a brief idea right here. The idea is, if you have an HR diagram, you can use that this method called spectroscopic parallax to measure the distances, right? Now I will talk more about this if the time permits, but you need to know about this method, right? So we are very familiar with that one. And then there is something called moving cluster method to measure the distances. So I'm not going to talk about that. So what I want to show you is there is another method that we used to call as period luminosity relationship to measure the distances to galaxies, right? And this is actually the first method that we have used to decide or to discover galaxies other than the Milky Way. And I will talk about that in the next section when we talk about galaxies. Right now, from you, basically, I want you to remember this one, the parallax method. That is the most basic method, and it is very important, and we have discussed about that. And also, you can read too about this spectroscopic parallax method, and if time permits, I will give you more details. And you don't need to worry about this one. Moving cluster method, I am not going to discuss with you. But I will be discussing some of these things separately with special degree students. And then this period luminosity relationship, we will use that, and we will apply to find the distances when we are talking about galaxies in the next section and probably next week. And here is the type 1a supernova. And you can see that there are, the way that we actually detect this is, as I have mentioned here, type 1a supernovae very consistent with their energy output, right? These curves are very consistent. And this method of finding distances takes the advantage of similarity type 1a light curves. The thing is, when you look at the light curve of supernova, which is the light curve means you are basically measuring the brightness of the supernova with the time, right? So each day you go and measure the brightness and have a dot here in the graph, and then you will get a light curve like this. So what that means is the light will increase and then decrease, right? And so as you see in the following figure right here, there is a clear relationship between the peak brightness and the rate of declining in the light curve, right? The brighter the peak brightness, the slower it declines. And you can see that all of these curves have a peak, and when the peak is higher, it declines slowly, right? If the peak is lower, it declines faster, right? So there is a relationship like that. And using this information, you can measure the distance. Now, when you look at most type 1A supernova, they reach to their maximum brightness in blue and visual bands. And I remember, I hope that I have talked about filters, right? This is like using a blue filter and a visual filter. Their absolute magnitude values are determined, and we know those values, that is 19.3 plus or minus 0.3, which means there can be an error of plus or minus 0.3. But this value we know for sure, right? They are true value, absolute magnitude value, right? And the idea is, I don't want you to know all this information, but I have mentioned it here in case if you are interested to get in detail, because there is a way that you can relate all these curves together to get, there is a relation between these maximum peaks. But in general, what you need to know is all these type 1A supernovas will have a maximum brightness in blue and visual bands. When you have that value will be minus 19.3, right? So that is the value that we are going to use to find the distances, right? Now, idea of these two curves are actually there is something called stretch factor, where you can apply the stretch factor and make all these curves coincide on this graph, right? You don't need to worry about that. That's something extra. But what you need to know here is, from this method, you can go for distance even greater than gigaparsecs, right? And the most distant supernova type 1A that we know is around this much of distance, right? Now, I have an example here to show you how you can use these type 1A supernova to find the distance to a galaxy, right? It's an example. There is a type 1A supernova called SN 1963P. That is the name given for that particular supernova in the galaxy NGC 1084, right? This is the name of the galaxy. And when you observe the supernova in this galaxy, it had an apparent blue magnitude which is equal to 14.0 at the peak brilliance, which means this peak value right here, this peak value is 14.0, and this is the apparent magnitude, right? And then there is an extinction correction of 0.49 magnitude to that particular galaxy, right? Now, what that means is, if you remember from the previous lectures, I have mentioned what is extinction means, right? Extinction means this absorption of light that comes when the light goes to these dust areas. Some of the light get absorbed and some get scattered. And because of that, when we observe from the Earth, the light normally get dims, right? Which means if the absolute if the brightness that you see is let's say 10 in the magnitude scale, that particular object should be actually brighter than that, right? So you have to do a correction for that. And for that, you need to know this extinction correction value, that is 0.49 magnitude. And there is nothing special here, right? Even the words that I have mentioned here as extinction correction, the idea is there is a the objects get dimmed because of this atmospheric effect called extinction. And if you know the amount, you can take that amount into the calculation, right? So that is the idea. And if you remember this equation right here, the apparent magnitude is equal to absolute magnitude plus 5 log d minus 5 and then plus a. And this is what we called as the extinction, right? So you have to add that. Yeah, if you are given an extinction correction. But for example, in the exam, if you are not given something like that, you don't need to worry about this, right? So then the equation should be something like, so let me write that here. So then the equation should be something like this, right? So you don't need to worry about the extension. I mean, if you are given an extension value like 0.59 or something like that, you need to add that correction to the equation, right? That's the idea. And under normal circumstances, this is the equation that we learned in one of those lectures previously, right? Then you can convert this into get this particular shape. And I have considered the extension correction here because it is given in the problem. So that my equation will be something like this. And the distance will be now, we know the apparent magnitude because that is what we can measure. And at the same time, this value right here, minus 19.3. So that comes from this information right here, because this is a constant for any supernova. Right? So this is why you can use these supernovas effectively to measure the distances, because this value we already know, right? Because all these supernovas will have the same absolute magnitude at the maximum brightness, right? So that value is a constant, minus 19.3. So all you need to do is you have to plug it here, minus 19.3. Right? Now, if this is needed in an exam, I am going to give you this value, so you don't need to remember it, right? So that value will be given at some place, maybe at the beginning of the question paper with all these constants. This will be also given so that whenever needed, you can use it, right? So that is the idea. And all you need to plug that value and then find the distance. And once you find the distance, it came as this much of parsecs, and this will be around 36.47 megaparsecs if you convert it, right? And right, so this is an example how to measure the distances to galaxies that are so far away using this information from the type 1A supernova, right? So I hope this is clear for everyone. And let me now go back into the presentation. Right. So now I have shared the presentation and I can see, I hope that all of you can see it. Right, the next question is, now we know different types of supernovas and how type 1A supernova can be used to measure the distances. Now let's see how we can observe these supernovas, right? So if you consider supernovas, as you can see, they are extremely bright, which gives off very much light, which is probably equivalent to billions of stars. And because of that, when a supernova occurs in our own galaxy, we should be able to, even see it from the naked eye. Right? Now, in last month, there was a nova that has occurred in our galaxy, and this was Not sure whether in our galaxy or in a different galaxy, but this was observable for countries in northern hemisphere, but not for us because it is very low in our horizon. Now, if you go back to the recorded history, there are 6 supernovae have been observed in our own Milky Way, right? And the first of these took place in AD 185, and this event was very bright. Even you could see it during the day at that time, according to the history. And there is this second one called K.V.S supernova, which is occurred in 1054. And this appearance is well recorded by some of the Chinese and Middle Eastern astronomers, and also by the people in North America. And the most recent observation of a supernova in our own galaxy is in 1604. Now you can see that when you look at our galaxy, it seems to be they are not as common as other events, right? Now the next question is, are these supernovas and then rare events, right? Now what we know up to now is, on average, one supernova explosion occurs somewhere in the Milky Way galaxy every 25 to 100 years, right? Now the strange thing is, we have not observed any supernova in our own galaxy since the invention of the telescope, right? So the last one was in 1604, and this is before the invention of the telescope, and we have not observed any supernova explosion in our galaxy after we invent the telescope, which is kind of interesting, right? And this may be either we have been exceptionally unlucky, or more likely that the recent explosions have taken place in parts of the galaxy where the interstellar dust block the light from reaching us. Now, when you consider our own galaxy, we can only see the galaxy in some directions only. So there are directions that we cannot see anything. So that is due to this interstellar dust. So they block the light from reaching us, right? Maybe there is a supernova that occurs in that region that we cannot see. Right? So that could be one of the reasons. Now, the thing is, these supernova explosions, you cannot predict, right? So these are like, like a chance event, right? So you cannot predict it. There is no way that we can tell that when will be the next supernova occur, right? Now, around the world, there are a large number of professionals and amateur astronomers that they keep sharp lookout for new stars that appear overnight, right? Hoping to be the first to spot the next guest star in our sky and make a little history themselves. Now, this is something that you could do as well. I mean, finding supernovas are very, very rare, and if you can detect one, you will be famous, right? The only thing that you have to look at is look at the sky and then observe it continuously to look for new bright stars that were not there in the previous day. Okay? So if there is a star that suddenly appears very brightly on the sky, which was not there on the previous day, which means there is a supernova explosion, right? Most probably it can be a supernova explosion, and that is kind of a more general way of finding one, right? Now, even though we have not seen any kind of supernova in our own galaxy for the past few centuries, in 1987, there was an astronomer in Chile who witnessed a supernova in a small galactic neighborhood of the Milky Way, which we called as the Large Magellanic Cloud. And this Large Magellanic Cloud is a galaxy, which is a galaxy that is very close by. And I will show you Large Magellanic Cloud in my next lectures about galaxies. And this is, we cannot clearly see Large Magellanic Cloud from here because it's a galaxy in the southern hemisphere. And he named the supernova as SN 1987A, which is one of the famous supernovas in recent past. And the reason is that this was the nearest and brightest supernova we have seen in modern times, right? And it was easily visible to the naked eye. Even you go outside and look at it, this supernova was visible at that time. And what we know now is what you have behind the supernova is a supergiant or blue supergiant star, right? And so what astronomers have done is, once they observe the supernova, they have been monitoring its expanding remnants. Right, so this is a Hubble telescope image of supernova 1987A. It is taken in a later year, and now once astronomers observed the supernova 1987A, they combine different theories and also these observations now they have at different wavelengths, and they reconstructed the life story of this particular star that became a supernova 1987A, right? Now from the knowledge that you have up to now, you know that how a supernova occurs, right? Basically supernova occurs by having this high mass star or a low mass star as a white dwarf going through a process, and then there will be explosion, right? So which means the in the heart of the supernova, or the fundamental object that you have behind the supernova is always a star, right? It's an explosive event, and what you can do when you have a supernova, you can get a lot of data in different wavelengths, and then you combine these theories and observations to build up and see what has happened to this particular star for in order to become, or in order to have it as a supernova at the end, right? Now, if you consider this particular supernova 1987A, astronomers have constructed its different phases of its life based on the data that they have, and according to that, this particular star that lead to the supernova 1987A have spent around 8 times 10 to the power 6 years by fusing hydrogen, and then fusing helium, it's 10 to the power 6 years again, and carbon fusion took 2000 years, neon fusion 6 months, oxygen fusion 1 year, and silicon fusion days, and then core collapse happens 10th of a second, right? Now what you need to get from here is that when you go for each step down, things happen very quickly, right? So I remember that I have mentioned it in theory as well, but astronomers have not only like and did that, they have also constructed they have also collected a lot of information about this supernova and have constructed this table so that you can get an idea that for each phase, when you go down to become a supernova, each phase happens quickly than the previous one, right? And you can see the density of the star also increases when you go down, right? At the same time, the temperature also increases, right? Right. Now, this is another supernova that we have observed very recently. This is called supernova 2014J. This is again an image of a supernova 2014J located in M82 or Messier 82, again a galaxy. And this is known as the Sika galaxy. And the image is again taken from Hubble Space Telescope. And then most importantly, this is a type 1A supernova, right? And you know that type 1A supernovas are very important to measure the distances to a particular galaxy. And once they detected, they have measured the distance using the method that we discussed earlier. And the distance was around 11.5 million light years from Earth. Right? And this is the closest supernova of type 1A discovered in the past few decades. Right? And you can see that is why it is important. Right. Now that's some of the evidences that we have about supernova observations. Now, you know that now we have a very modern type detectors and telescopes, and because of that, it is possible to detect supernovas in these distant galaxies. Right. Now we have observed thousands of these kind of supernovas, and most of them are actually billions of light years away from us. And we have detected both type 1A and type 2 supernovas, even though type 1A supernova is more important in measuring distances. And on average, what we now can tell is that both type of these supernovas are estimated to occur approximately once every 40 years per galaxy. Right? For each galaxy, there may be one for each 40 years. Now that's all about active supernovas. But when you have a supernova, you know, it will brighten up for some time and then will fade away, right? And then you cannot see it. However, so there are only bright, so these are only bright for few months. But the debris that these supernovas create, we can observe those for thousands of years, right? And for example, if you look at the Crab supernova, there is also something called Crab nebula, right? So that nebula is a supernova remnant from the Crab supernova, which has happened thousands of years ago. And you cannot observe the supernova now, but you can observe the Crab nebula, right? Which came as a result of the supernova explosion. And you can actually look at this Crab nebula even from a smaller telescope, right? And so here are some examples of images for these type of supernova remnants. You can actually read through about those. And this will actually conclude this section about high mass stars and supernova explosions. And let me start about, right, does anybody have any questions up to here based on what we have told? Before we go into the next section. No questions. Okay, so let me then start at least a few slides in the next section, which is about neutron stars and black holes. Right? Share the right, so I hope all of you can see my slides about neutron stars and black holes. Right now, remember that we have talked what would happen to these heavy stars, and we discussed that there will be a series of process that goes through, and as a result of that, you will have a type 2 supernova explosion for these high mass stars. But after this type 2 supernova explosions, it will remove all these materials outside, but you will have this dense core at the end, right? So there will be a core which is very dense, right? And remember that I told you that at the central region of this high mass stars, now you have only neutrons, right? And because of that, these tiny cores with highly compressed neutrons are called as neutron stars. So that's how the name came, right? So you had this very high mass star, and which goes through series of thermonuclear fusion reactions, and at the end you have iron at the center. And once the temperature increases more and more due to the contraction of the gravity, there will be a process called photodisintegration that could happen inside the star. So what that means is this iron can also break up into electrons, protons, and neutrons. And then at the end, you have electrons, protons, and neutrons. And then electrons and protons combine to form neutrons. And because of that, at the end, you have a dense core of neutrons, right? And this is why when materials plunging inwards, they bounce back, which created this type 2 supernova. But after this explosion, you will still have this core region of the star, which is basically compressed neutrons, right? And that particular object is called as a neutron star. And as you can see from the information that these objects should be extremely dense, right? Now, if I can give an example for this density, so they are typically about 20 kilometers in diameter, but more massive than the sun, right? Now, sun is huge, right? It has a huge diameter. Now, these objects that we consider as neutron stars, they are actually even more massive than the sun, but their typical diameter is around 20 kilometers, right? Now, this is a very small object compared to the astronomical scale, right? And what happens is this makes them a billion times denser than white dwarfs and 10 trillion times denser than the Earth, right? Now, this is why you get this high density, because you have a set neutron stars compressed together at the central region, and these objects are extremely dense because of that. Right now, we will move on to talk about discovery of pulsars, right? So there is another type of object called pulsars. However, these pulsars are neutron stars are connected. Pulsars and neutron stars are connected in a certain way. That is, as you know, neutron stars are extremely small and they are very faint, right? Because you don't have anything to give off light. You just have a neutron core there, right? Now, because of that, it is very hard to detect these neutron stars. So astronomers have, predicted their existence, but they were almost undetectable until this year, 1967, where a few astronomers using a radio telescope, they detected an object that was giving off rapid pulses of radio waves, right? And these pulses were detected once every 1.337311 seconds. And you can see that this periodicity is very, very accurate. And each of these pulses last around 0.01 seconds. So you need to have a very accurate clocks to measure these kind of things. However, this is what has happened in 1967. There were a set of astronomers who were using a radio telescope, and they suddenly detected an object which was giving off these rapid pulses, and pulses are very uniform, right? Which means you kind of have the same periodicity for the pulses. And you can see that up to now, we have detected some kind of object where it emits rapid radio pulses, but we don't know what it is, right? And this is how those stars were pulsating or making pulses, which clearly shows you that there is a regular periodicity. And now let's see how these pulsars are connected to neutron stars, right? Now, in the first place, pulsars appear to be found in blank places of the sky. So that is what people thought. Pulsars appear, but they are very blank places on the sky, and there may be nothing there, just the pulsar only, right? And then we have found a neutron or a pulsar right at the heart of the Crab Nebula, and we know that there is a neutron star in the Crab Nebula because it's a site for type 1 is it's a site for supernova explosion, right? So once you had a supernova explosion, especially for the type 2, you should have a remaining neutron star there, right? But they are very weak or they are very faint, so that you cannot see those, right? And at the same time, there is a connection between a pulsar and a neutron star, right? So that connection is that neutron star have a strong magnetic field which can accelerate charged particles from their magnetic poles, and this result in the emission of radio radiation, right? And then you have to detect that, and that is basically what we do to detect actual neutron stars. And once again, remember that pulsar is not a new kind of object, right? So what has happened was these astronomers who were using a radio telescope, they have detected a rapid object that make these rapid pulses, right? And then they did a little more research and found that there was a similar kind of object at the heart of Crab Nebula, which means this object is again making these pulses. But at the same time, in the Crab Nebula, we know that there should be a neutron star, right? Because Crab Nebula is a site for one of these supernova explosions, and if it is a type 2 supernova explosion, we know that you should have a neutron star after the explosion, right? And because of that, people thought that there should be a connection between this neutron star and the pulsars they are observing, right? Now, what has actually happened is neutron stars have these strong magnetic fields, and they can accelerate charged particles from their magnetic fields, right? And I guess who have done some kind of physics should know about this, right? Even from the aerial physics, that once you have a magnetic field, it can accelerate these charged particles, right? And right now, and because of that, we know that these rotating, actually pulsars are, now we know that pulsars are these rotating neutron stars, right? Now neutron stars rotate very rapidly, and that is actually a consequence of conservation of angular momentum, right? When the original star collapsed, I guess all of you can understand it from aerial physics. When you have an object, a large object, which is, goes around its own axis, and if you lose some of this mass, and if the radius of the objects gets smaller, it should move faster, right? So because its moment of inertia is smaller now, and this is an application of the angular momentum. And there is actually a nice way of explaining this neutron stars and pulsars. And here is a neutron. Here is a neutron star from the blue color, and it has a magnetic field from these red lines. You can see a magnetic field, and here is the rotation axis of the neutron star, which means the neutron star rotates around this particular axis. And when it is rotating, what happens is it has this beam of particles and radiation, right? Now this radiation is directed to a certain direction, right? So what can happen is that when this body rotates on its own axis, this radiation cone right here could move up to here and cover the earth like this, right? So if that happens, we will also observe these rapid pulses, right? But this is one possibility that can happen, and it is also possible that at a particular time it is not directed towards the earth's surface, right? Both those things can happen. But when we observe these pulsars, so these are the pulsars, right? So if it happened to be directed towards the earth, then we will observe pulsars, right? So that is how pulsars and neutron stars are connected. But there may be times that this pulsar that we see may not be directed towards the earth, right? If that is the case, you will still have the neutron star, but you will not see a pulsar, right? And because of that, we have this specific sentence right here. While all pulsars are thought to be neutron stars, the converse is not true, right? I mean, if you have a pulsar, we can straight away decide that, okay, there should be a neutron star, right? But there may be a neutron star that doesn't give you pulsars, which means by detecting all these pulsars, we cannot decide about the existence of all the neutron stars, right? As you can see here, here is the pulsar. This region, as it emits, you may detect it, you may not detect the pulsar, right? But the neutron star is still there. Now, this is why we used to tell that all pulsars are neutron stars, but all neutron stars may be not pulsars, right? Right. Now, if you compare then now a neutron star and a white dwarf, you can see the differences, right? White dwarf always has a mass less than 1.4, but for the neutron star, the mass will be between 1.4 and 3, right? And look at the radius. For a white dwarf, the radius is 7,000 kilometers, but for the neutron star, it will be 10 kilometers, right? And you can see the difference. And the density is the same. Also, there is a huge difference. For the white dwarf is 8 times 10 to the power of 5 grams per cubic centimeter. But when you look at the neutron star, it is 10 to the power 14 grams per cubic centimeter, right? And you can see that neutron stars are very dense, very small, and at the same time, mass is actually a little larger than the sun, right? Not the sun, sorry, mass is actually larger than the white dwarf, not the sun. Now, these are the major differences between the white dwarf, which is the endpoint of a low mass star, and neutron star, which is one of the endpoints of these high mass stars, right? Because neutron star, high mass stars could become a black hole as well, right? By going going to the next phase. And here is another two examples for supernova remnants. And as you see that in order to detect a neutron star, you should detect a pulsar first, right? So if you detect a pulsar, you can confirm that there should be a neutron star at that particular position, right? That is the simplest method actually that we can detect neutron stars, right? But there are other ways of detecting neutron stars because the pulsar phenomena can be seen at the other wavelengths, including visible light, and there are sometimes, the telescopes like Hubble Space Telescopes may be able to detect these very faint stars, right? Because the technology is higher and this particular telescope is in this space, right? Which means it can avoid the atmosphere and observe these faint stars, right? Let me finish these few slides so that we can start from the black holes on the next day, right? And another way of actually detecting a neutron star is, if, let's say you have a neutron star right here, and you have an ordinary star which is very nearby, right? Now what can happen is the gas escaping this star to go into the neutron star and then they rotate around it, right? So this will increase, you know, I mean, they will actually infalling, there is infalling matter, and this will be compressed and heated to very large temperatures. When something is heated, then it emits X-rays, right here. Right? So these are like simple physics that we apply here. So when something heats up, it will emit X-rays. So which means if you can detect beams of X-rays from an X-ray telescope like this and this, then you can also decide that there may be a neutron star at that particular place, right? So you can use pulsars to detect it, and or neutrons or these X-rays, right? If you, I mean, you can detect it from X-rays only if you have a companion star nearby, an ordinary star, which can give matter to these neutron stars. And here is an image of the Crab Nebula. So what I need to mention here is these pulsar phenomena also can be seen as other wavelengths. You can just read through it. And there is a slide about the gamma rays and then about the black holes. So let me stop from here and I will briefly talk about gamma rays if time permits. Then we can start talking about black holes and some of these simple, some of the theories that goes with the black hole, right? The theories like theory of general relativity, I will very briefly introduce you what those mean, right, without going into mathematics, right? Anybody have any questions up here? Is there anyone who questions up here? No, you can even ask from Signal if you prefer, that should be fine. Right, then there is a small message for you. I will be doing a guest lecture for this SED Sri Lanka about the galaxies at some point in a weekend. And if anyone is interested, you can join with that. I think the date is not yet fixed, but once the date is fixed, I may send you the link. If anybody is interested, you may join with that. Maybe helpful for your classes as well, because I will be basically talking more or less the same thing and some of these practical things about my personal observations. Right, so if any of you do not have a question, I'm going to stop right now. And so I heard that there are some of you have issues, which means that you have not completed these previous 2 assignments, and I may give another 2 new assignments, and I will inform you about that. And then we will, and also for those who could not complete the previous ones, once I get all the details, I may reopen it at some point, right? For those who have not completed those 2 assignments as well. Right. So thank you everyone. If you do not have any questions, and we will meet again on next Thursday morning at 7 a.m. right, to talk about black holes, and then we will move on to talk about exoplanets and stellar motion in the evening, and probably after that we can probably go and talk about galaxies and galaxy clusters. Right. Thank you.